When we started this chapter, we began by performing the Hooke's Law Lab. And in the Hooke's Law Lab, we were able to derive the equation called Hooke's Law, which is the relationship between force and stretch for a spring. We then used that, we found the area under the curve to be the energy stored in the spring, and that was our bridge from talking about springs into energy. Most of this chapter is about energy. So in this section, we're just going to define the different types of energy that we're going to be talking about in physics. So that's all we're doing here. So there's not going to be math, just basically definitions and ideas. So to start with, what is energy? We always rely back on the basic definition for energy, that where energy is the ability to do work or produce change. You've probably heard that before. That's the most common definition given in chemistry or physical science. You've likely had that definition for energy before. To produce change is really more the focus in chemistry, where you look at different chemical reactions and what they do. In physics, we focus more on the ability to do work. And later in this presentation, I'm going to define for you what it means to do work in physics. So for energy, the unit, the SI unit for energy is always joules, never anything else. A joule is defined by a Newton times a meter. That's something that you should know. So if you ever do a story problem and you end up with a unit Newton meter, you should automatically know that that's a joule. You should also remember that a Newton breaks down into a kilogram meter per second squared. So those are both things that you should know as far as units, and they will show up on the semester test, so they're definitely worth knowing. Okay, a couple things about energy. One is that you probably remember that energy cannot be created or destroyed. That's a law of conservation of energy, and we use that an awful lot in this chapter to solve story problems. Another thing about energy is that there's a lot of different ways that you can store energy. So we're going to look at the three mechanisms in physics that we're going to store energy in, although there are a few others in different disciplines. For example, chemical energy, that is the storage of energy, but we don't really talk about it in physics. So the first one that we're going to talk about here is one that we actually defined with the Hooke's Law Lab, but I thought we'd put all three of them together so you'd have them neatly compiled in your notes for reference. So I'll go through this one quickly. So for a spring, we have elastic potential energy, and I have both the symbols there. We stick to the notation of the capital E with the EL subscripted for elastic potential energy, but you may see it the other way somewhere else. That's why I left that on there. Okay, so elastic potential energy, you have to have a spring in order to have that. So if you stretch a spring, it then has the potential to do something with the energy that you've put in it. So in the case of this picture down at the bottom, if I stretch this spring and I have a mass, if I were then to release the spring, or if I were to take the mass off, that spring would bounce up. So that would be an effect that it would have by releasing that energy that has been stored. So here's our equation for elastic energy, and I put for all of these the unit that you should most likely have these in when you do problem solving. Although I mentioned with the spring, if you have both of these in centimeters or something else, it's okay. But normally this is how you're going to see them. Okay, one thing about this chapter is we do end up with a couple different equations for energy. So it is important to know when to use which one. So for this one, anytime you have a spring in a problem, this is an equation that you're going to use. I think this one's fairly straightforward in that. So the second one we're going to look at is kinetic energy. Kinetic, you know, means moving. So you know you have kinetic energy whenever something is in motion. So energy stored as motion, and the equation is 1/2 mv squared. Here the mass does have to be in kilograms, and the velocity has to be in meters per second. Physics problems often like to put the velocity in something else, like kilometers per hour, and make you convert it, so do pay attention to that. Same thing with the mass. Sometimes they give it to you in grams, so make sure that your units always work out. When do you use this one? Whenever you have something moving, either at the beginning of the problem or the end of the problem. And we'll do some examples where we'll see when to use which one. Okay? So the third one here is gravitational potential energy. So that's big E subscript G, or GPE in most other curriculums. So this is energy stored as a result of an object's position. So what that means is if you have a brick and you put it up high in the air, now the brick has energy that it didn't have before. If you had the brick on the floor and you didn't do anything with it, nothing would happen, right? It just sits there. But if you pick the brick up high and you let it go, it's going to do something because you've given it energy by picking it up. So it's going to drop and fall and hit you on the toe, and then that energy would be transferred into your toe. Okay, I like the snowboarder thing at the bottom. I noticed the Winter Olympics is coming up, so there's my salute to the Winter Olympics. Scary. Okay, so here's our equation for gravitational potential energy. So it's mgh, simple enough. And h here has to be the change in height. Now it's not an absolute height. If you were in a problem, if you started at 10 meters and you end at 15 meters, you would use 5 there because it's not your actual height, just your change in height. And I'll explain that a little bit more here. One thing that's different about gravitational energy as compared to the other ones, say kinetic energy, if your velocity is 0, you absolutely have no kinetic energy. There's nothing to talk about there. But if you have a height, you may or may not say that you have gravitational potential energy. And here's what I mean by that. If you're standing outside in your yard, and your height then would be 0. So you would say you have 0 gravitational potential energy. But then if you were to dig a hole and jump in it, all of a sudden your height is lower than it started before. So you could either say the bottom of your new hole is 0 for height, or you could say your height is negative if you call the ground your 0 spot. You see what I mean by that? It depends on, it doesn't really matter where you are, it matters how your height changes as far as your change in gravitational potential energy. So it's not an absolute number, it's a relative number based on your position. That doesn't mean it's not real and that it doesn't exist. It just means that how you define it is based on the change in height, not the absolute height. Okay, whenever you use this one, there has to be a change in height. So if you have a problem where you start and end at the exact same height, you don't even have to worry about this because you may say that you have gravitational potential energy, but if it doesn't change, then it doesn't matter. It isn't relative. Okay. The last thing we're going to talk about in this section is work. Now, work is different from the other 3, and that's why I have it set apart here, is the other 3 are what you call an energy storage mechanism. So you can store energy in kinetic energy. You can store energy in a spring. You can store energy by height, like the dropping the brick thing. Work is different because you're not storing energy in a system. You are adding or subtracting energy from that system. So I'm going to define it in 2 different ways here and try to explain. So the basic physics definition for work, there's a couple that actually work pretty well. But as far as the equation goes, and then we'll talk more about the concept, as far as the equation goes, you have work when you have force that moves something in the direction of that force. And I actually put 2 equations on here. The normal way that you'll see it from me, or it just in this curriculum, is work equals Fx. And in that equation, the x has to be in the direction of the force. Sometimes you'll see it written here with the trig, with the cosine. All that means is that if you take a force cosine theta, you're finding the x component of that force, right? Just like we've been doing with all the vectors and things all year. So you might see the equation written that way, means the same thing, where this x is the x component of the force. This would be the force at an angle, and you would take the the cosine theta of it to find the x component, okay? So same thing, but I thought I'd let you see that. Work is also in joules because it actually is energy. It's just a change in energy in a system. So your work is going to be force times distance. So that's not an extra x, that's supposed to be a times sign there. Okay, a couple things about work that is tricky. One is that if you push really hard on something but it doesn't move, then by the physics definition of work that we just talked about, you haven't done any work. So if you push against the wall with all of your might, you break a sweat, you get your heart rate up, all of that, if you haven't moved the wall, you haven't actually done any physics work. Okay, so by definition, work has to move something. The other thing that's a little bit tricky is that the force has to be in the same direction as the displacement, and that reflects back to that cosine theta I had on the last slide. So like my little picture here, if you're carrying a box and you're moving at a constant speed, and they use constant velocity here to show no acceleration means there's no net force in the x direction, but the force that you have is to keep the box up. So you're resisting the force of gravity. But that force is perpendicular to the direction that you're going. So in that case, there again is no physics work, which think again about force cosine theta. That's not really going to work out for you here when you're perpendicular, okay? So that is one way to look at work. The other thing I wanted to talk about is here is that work is also defined as a change in mechanical energy into a system. It's the same thing, it's just we're not focusing on the equation part of it here. So my silly little example, it's kind of a creepy picture actually. Let's say a weightlifter, so he picks up the barbell. So when the barbell is on the ground, the barbell has no energy, right? If you look at the system of energy, what is my system? The system is whatever objects you're focusing on in a problem. So here the system would really be the barbell. You could do the barbell and the guy if you wanted, but let's just talk about the barbell. So if the barbell's on the ground, it has no energy. Once he picks it up, he's applying a force, moving at a distance. So he has done work, force times distance, and now the barbell does have energy. The kind of energy that it has is gravitational potential energy, since he's changed the height of the barbell. So you know he's added energy to it, because if he let go, it's going to drop and speed up until it hits the ground, gaining kinetic energy until it hits the ground. Okay, so another way to look at work then is the change in energy in a system. So if we'll look at a lot of different examples of this, but let's say you push a car a certain distance. The car, if its engine were dead, that's a classic example of a story problem in this chapter. When the battery's dead, it has no energy. But if you push it, you cause it to move. And when it's moving, it has kinetic energy. So you've pushed it a distance, had it gain kinetic energy. So you've done work on it. So that's the way that work happens, and we'll talk more about that as we go. But that's as much as I wanted to do here, was to do the definitions for each of the forms of energy.